we're going to investigate some things that happen when we draw the altitude to the hypotenuse in a right triangle. So we have a right triangle here, the large one, triangle ABC. From point C, if we draw a perpendicular segment to the line that contains segment AB, that would be considered an altitude. In the case of a right triangle, that altitude does actually intersect the opposite side. Notice D is not necessarily the midpoint of the hypotenuse. It might be, but in general, that cannot be assumed. Now, notice then that I have three triangles. The large triangle ABC that we originally started with, and then two smaller right triangles created by the addition of that altitude. Now, recall that if two triangles have angles so that one pair of angles in one triangle are congruent to one pair of angles in another triangle, the two triangles have to be similar. Remember, that's called asimilarity. Well, angle A is in both this smaller right triangle and the large triangle. Angle D, angle ADC, I guess we'd have to name it, is a right angle. And angle ACD, or B, excuse me, and the large triangle is a right angle. So there would be another pair of congruent angles between those two triangles. So we could say that triangle ACD is similar to triangle. Now A is going to correspond to A. Let's see, we go A to C. That's the hypotenuse in this right triangle, and we end at the right angle. So let's see, the hypotenuse in the large right triangle is segment AB, and at the right angle C. And that would be by asimilarity. Now, let's turn our attention to this right triangle to the left, the smaller one. We don't have it shown here, but if we have a right angle ADC, angle BCD is also going to be a right angle. Our definition of perpendicular, form right angles at the intersection point. Angle B is in both this smaller triangle to the left and the large right triangle, so angle B is congruent to itself by the reflexive property. So we could say that triangle BCD is similar to triangle, let's see, B would correspond to itself. So we go B to C, that's the hypotenuse in this right triangle, and we end at the right angle. So the hypotenuse in the large right triangle and at the right angle, we'd go BAC. Now, notice these two smaller triangles are similar to the large triangle. Well, if two triangles are similar to a third triangle, then those two triangles have to be similar as well. So these two smaller triangles have to be similar. Let's see if we can match these up. If I use triangle ACD, let's see, A goes to A in this one goes to C. C goes to B. B in this one make sure I get this right. C goes to B. And B and this one goes to B. Okay. And then the right angle. So triangle ACD is similar to triangle CBD. The two smaller triangles are similar. Now, that's theorem 8-1. If the altitude to the hypotenuse in a right triangle is drawn, then it divides the right triangle into two smaller triangles that are similar to the large triangle and to each other. Now, notice this segment CD. Okay, segment CD is in both of these smaller triangles. If I match corresponding parts, CD in this triangle, ACD, corresponds to CB in the other. No, excuse me, BD. Now we need another one in this. Let's say we look at segment AD. Well, AD as a distance in this triangle corresponds to BD. No, it doesn't. It corresponds to CD. Sorry about that. Notice what happens when we do our cross products. CD times CD would be the distance from C to D squared. And here we have the distance from B to D times the distance from A to D. So the distance from C to D is the square root of the distance from B to D times the distance from A to D. In other words, that segment's length is the geometric mean between those two segments' lengths. So let's suppose we look at this problem. I have the altitude to the hypotenuse drawn in this right triangle. This would be the altitude to the hypotenuse in this large right triangle. What we just talked about would say that this length is the geometric mean between those two lengths. So in other words, 8 is the square root of 14 times x. So thinking about undoing operations here. Okay, we multiply by 14, take the square root. So first of all, we're going to undo the square root. We can undo the square root by squaring. So if we square 8, we get 64. Square the square root, we get 14x. Divide both sides by 14. So x would equal 64 divided by 14. I can see both of those are divisible by 2. So x would equal 32 sevenths. If we'd want to write that as 4 and 4 sevenths, that's fine. But that's good. So here is an application of the altitude geometric mean theorem. The altitude in the right triangle is the geometric mean between the two segments of the hypotenuse formed when we put that altitude into our triangle. Now, going back to our original picture, we know that each of these smaller triangles is similar to the large triangle. Let's look at this one. Segment AC the altitude in triangle ACD corresponds to segment AB. And then segment AD in this smaller triangle corresponds to segment AC. See how our work with proportions has been so important? So if we do cross products, we'd have the distance from A to C squared equals the distance from A to B times the distance from A to D. So the distance from A to C is the square root of the distance from A to B times the distance from A to D. Now, algebraically, it'd be positive or negative the square root, but we know these are distances. Notice what this is saying. It's saying the length of a leg of this right triangle is the geometric mean between the hypotenuse and the segment of the hypotenuse that's adjacent to that leg. Let's see if that's also true for this leg of our large right triangle. Well, segment BC from triangle BCD is going to correspond to segment BA's length from the large right triangle. And then another segment from triangle BCD, let's say segment BD, its length will correspond to the distance from B to C. And so with our cross products, BC times BC gives us that distance squared equals the distance from B to A times the distance from B to D. So the distance from B to C is the positive square root of the distance from B to A times the distance from B to D. In other words, this leg of our right triangle is the geometric mean between the length of the hypotenuse, that's segment BA's length, and the length of the segment of the hypotenuse adjacent to that leg, segment BD's length. So, let's look at another theorem. That would be, or an application of that theorem. That would be what we would see in Theorem 8-2, which is the leg geometric mean theorem. Now, let's suppose that I have a triangle labeled like this. We have three values, x, y, and z, that we need to find. Notice that x is the length of, I have to label this here, the altitude to the hypotenuse of the large right triangle. Y and z are the lengths of the two legs of the large right triangle, respectively. So, the altitude geometric mean theorem would say that x is the square root of 7 times 4. Now, I'm actually not going to multiply those together because I know 4 in this case is a square. So that's the square root of 4 times the square root of 7. So the square root of 4, is I would have 2 times the square root of 7. We could have multiplied those together, gotten 28 under the square root, have done our prime factorization, and we would have found the same thing. Now, y is a leg of this right triangle, and we know that it's the geometric mean between the length of the hypotenuse, and here's where we have to be careful. The length of the hypotenuse here would be 11. And the segment of the hypotenuse that's adjacent to that leg. 4 is adjacent to this length of y. Again, I could multiply those together so we'd have the square root of 44, but 4 in this case is a square, so I can write the square root of 11 times 4 as the square root of 4 times the square root of 11. So y is going to be 2 times the square root of 11. Finally, z is the length of a leg of this right triangle. And Theorem 8-2, the leg geometric mean theorem, says it's the geometric mean between the hypotenuse, remember that has a length of 11, and the segment of the hypotenuse adjacent to that leg, which is a length of 7. Now, neither 11 nor 7 are squares, so let's go ahead and multiply those together. So we'd have the square root of 77. Now, the prime factorization, okay, 2 doesn't divide in, 7 plus 7 is 14, so 3 doesn't divide in, doesn't end with 5 or 0, so 5 doesn't divide into that. 7 divides into that. Oh, 11's also prime, so there are no pairs of prime factors that we see there. So z equaling the square root of 77 would be as far as we could go there. That's all for that lesson.